everyone doing on this fine Tuesday? All right, Unit 7. We are now on the second half of our AP Stat course. So you have two packets. You have your notes packet and a packet of exercises and worksheets. As always, I start you with a vocab and tech page. So nothing new on the calculator this unit, but we have lots of new vocab. All right, so 7.1. We have a lot of vocab in 7.1. But what I'm going to do is I'm actually going to jump ahead a little bit. Down here it says, if you have not done so, complete the exercise, fire up chips, fire up poker chips though. All right, so what you're going to do, so I'm going to flip to the other packet. In the bag, there are 200 poker chips. And I know that because I counted them out. All right. 100 of them are red. I will tell you that. So 50% of the chips in here are red. The rest are a mix of blue, green, and white. Now, what we're going to do is we're going to figure out, you guys are going to figure out how many blue, green, and white there are. Now, the only reason I told you how many red there are is we're going to see how, if I didn't tell you how many red there were, how this method, you probably could figure it out, okay? So I tell you one of the values so that you can see that when we're done, if you had to estimate, hopefully you'll see how you would have estimated that half of them were red. And then if we can see that, then hopefully we'll trust our estimates on the other ones, okay? So what you're going to do, you are going to, while we're taking notes, so you guys are going to have to kind of do this quietly in the background, okay? You're going to take, and I'll start here with Madison. She's going to take 20 poker chips out of the bag, okay? So you're going to count out 20 poker chips, and you are going to count how many of each you have, okay? So I'm making this up. Let's say when Madison pulls out her 20 poker chips, she ends up with 12 of them are red out of the 20. So that would end up being 60%, okay? So you're going to do how many red, how many blue, how many green, how many white, and you're going to then calculate your percentages, and you're going to put them here. Then you got to put them back in the bag, pass them along, so then I don't care if you pass behind or across, whatever, but everyone's going to do it. The mistake that happened one year when I didn't explain it this carefully, I had the first person took 20 poker chips out of the bag, and I wasn't paying attention. They passed the bag, and then the next person took 20 of them out, and then the next person, and I'm like, no, I finally come, I'm like, no, you got to put them back. Okay, you got to put them back. So that's why I get you started on it now, so that by the time we actually get to that point in the notes, hopefully we're close to all of you being done, okay? So I will start. Now don't peek into the bag. Just pick out your 20 poker chips. Okay. All right. So while she's doing that, and Madison will have to get caught up on the notes, and and every time the bag gets passed, you're going to miss some of the notes. You'll have to back up and get caught up, whatever. Okay, so let's start talking about some of our definitions while the poker chips are being sent around. All right. I actually think we've talked about parameters and statistics before. I feel like that came out one of the Party Sabetti videos. But a parameter is a number that describes something about a population. A number that describes something about a population. And I'm pretty sure in her video, Party said something about remember your P's and Q's or something, okay? Or P's and S's, because basically, if you're talking about a population, P, then your values are called parameters, also P. So You could talk about the mean of the population, the standard deviation of the population, the interquartile range for the population. Okay, those are all called parameter. In statistical practice, the parameter is usually unknown. Okay, like right now, if I said, hey, what's the mean NWEA score for all the sophomores, in L'Anse Creuse? I don't know. But what I could do then is I could take a sample by just checking what the NWEA scores are from the people who are in this building. And then I could maybe try to estimate what everyone in L'Anse Creuse would have. So a statistic is a number that describes something about a sample. And I'm going to underline the letter S. So you could talk about the mean of the population. You could talk about the mean of your sample. You could talk about the standard deviation of your population, the standard deviation of your sample. Okay, so if you're talking about the population, all those values are called parameters. If you're talking about a sample, all those little values are called statistics. Okay, so back to my NWEA example. I could look up all the NWEA test scores that my sophomores got when they just took their test last week. I could figure out what the mean is. That could be considered a statistic because it could be one sample of 10th graders in all of L'Anse Creuse. I could then say, well, if the mean score was, and I'm making up this number, if the mean score was 300, I could now come back and say, well, I guess maybe that means if all the students in L'Anse Creuse were tested, maybe on average, they would all have about 300, okay? The value of a statistic often is used to estimate a parameter. We can't always know everything about a population. So we take a sample and then we figure out what the value of a statistic might be for the sample. And then we try to do statistical inference and go back and say, well, I think that must be true with the whole population. You guys are doing samples right now. You're taking 20 poker chips, a sample, out of a population of 200 poker chips, okay? Explain the difference between P and P hat. The word P stands for a proportion, okay? The word P stands for proportion. P stands for proportion. But if it's just regular P, that's the proportion, okay? Remember, a proportion is another word for a percentage. If it's regular P, that's from the population. If it's P hat, that's from a sample. So what you are calculating right now, you are calculating a whole bunch of P hat values, okay? You are calculating P hat values because you're taking only 20 poker chips out of the population of 200, and then you are calculating how many red do I have. So you're calculating a proportion, 60% out of just the sample. You don't have the entire population. You don't know all the values about the population. Now, in this example, however, you do know this. You know that P really is 50%. We know that because I told you that, and I didn't lie to you. I counted those poker chips out, okay? What we don't know is we don't know what the P value is for blue. We don't know the P value for green. We don't know the P value for white. You're going to get your P hat values, and we're going to see if we can figure out what P is, okay? Explain the difference between mu and X bar. Both of these stand for the mean. However, mu is the mean for the population. X bar is the mean for the sample. And I only use those two right here because in this class, those are the things that we will use the most. You could do, I shouldn't say that, but you could do, you have SX and you have sigma. Those are both standard deviations. But this is the standard deviation of the sample. This is the standard deviation of the population. Okay, we just use different symbols, whether we're dealing with a sample or whether we're dealing with a population. Now I'm going to say it. These are probably the three biggies that we use in this class. But I also can tell you, we focus on these even more than this one. Okay. So the first couple of examples are just, can you identify a population versus a sample, a parameter versus a statistic? So a pediatrician wants to know the 75th percentile, which is also Q3, remember? They want to know the 75th percentile for the distribution of heights of 10-year-old boys. She finds the heights of 50 patients, and she calculates Q3, 75th percentile, as 56 inches. All right. That right there, those 50 patients, that was her sample. She got information on 50 of her patients. Who is the entire population? All 10-year-old boys. So she knew it was not going to be possible for her to figure out what the heights were for every 10-year-old boy in the whole wide world. So she said, well, I'm just going to take a sample of 50 of them, and I'm going to calculate the 75th percentile, which she did. She calculated that Q3 was 56. The parameter would be Q3 for all 10-year-old boys. And you'll notice I don't have a special symbol for that. These we have special symbols for population versus sample because they're so commonly used. This we don't, okay? 75th percentile for the sample, 75th percentile for the population. We just say it in words. All right, part B. Pew Research Center is actually a very well-known research organization, and they asked over 1,100 almost teenagers and teenagers in the U.S. if they have a cell phone. Of the respondents, 71% yes. Ooh, how old do you think that data is? What would you, seriously, right now, if you had to guess, what do you think if we asked, what percent of this age person do you think have cell phones? Seriously, I would say probably, I'm going to put in the 90s. I would, if I had to guess. I think that's some really old data. But anyways, when the Pew Research Center asked those people, that was their sample. Those 1,102 12 to 17-year-olds, that was the sample. And that was a sample out of the population of all 12 to 17-year-olds. Now, what did the Pew Research Center find? They found that 71% said we have a cell phone. That is a p-hat value. It's a percentage, which is also called a proportion, but the 71% was just from the sample, so that's p-hat. So the parameter would be p, and that p would be the proportion of all 12 to 17-year-olds who have a cell phone. So we've talked about this before also, but it's worth repeating. There's this thing called sampling variability. Okay, you guys right now, you're all picking 20 poker chips out of the 200. Are you all going to get the same p-hat values? No. Every time you take a sample, okay, the Pew Research Center, when they sampled those 1,100 people, if they sampled a different 1,100 people, would they have come up with a 71%? Maybe not. Maybe they would have gotten only 60%. Maybe they would have gotten 80%. Sampling variability simply refers to statistics may change with different samples. And therein lies the whole concept of statistical inference. And that is, when we do statistics, and this is why I always tell you, we don't prove anything, because we know that every time we take a sample, our results could be a little bit different. Our hope is, if we set up a good sampling procedure, that we hope that our results can be trustworthy enough that we can say, okay, this is what we really think is happening, okay? All right, so if you have not done so, complete the exercise, fire up chips. Okay, and we're working on it. All right, we'll come back to that. We'll keep going because I think we're getting there with our chips. All right, an unbiased estimator. Okay, this is the goal of what we're learning how to do right now. An unbiased estimator is a statistic from a sampling distribution which you'll see is its own vocab word coming up. I probably should reorder this because I'm defining something using a word that you don't even know what it is yet. All right, a statistic from a sampling distribution that can be used to estimate a population parameter. So just to go the poker chip example, this is the reason I do these exercises, because I like to kind of give you a hands-on or a visual of what you're doing. You are doing a sampling procedure, okay? You are each sampling 20 poker chips out of those 200. You are figuring out 4 different p-hat values, the p-hat for red, white, blue, and green. What we are going to try to do is we are going to try to take those p-hat values and use them to estimate the true proportions, okay? Now, we know what the true proportion is for red. We know it's 50%. So we're going to see if your results would have led us to the 50% if we didn't know that already, okay? So an unbiased estimator just means that we can trust our sampling procedure, okay? There are some times that you can do the sampling procedure correctly, but you can't use the results, okay? We'll talk about that with our other exercise that we're going to do. All right, so what is a sampling distribution? Well, we'll get there. A population distribution, okay? The population distribution are all the actual parameters of a population. So we're going to get to that once we get through this. We're going to, and I'll share, we're going to estimate what we think the true P's are for our poker chips. Okay, but I can't tell you yet. But we'll come back and I'll talk about population distribution after we finish our exercise. A sampling distribution is the distribution of one subset of a population distribution. And I'm going to put a star here because this is actually what we're going to make. We're going to make, oh, no, I'm not putting a star there. We're going to put a star here. And I need to amend my definition because I just wrote the definition for the approximate. A sampling distribution is the distribution of all possible subsets of a population distribution, and an approximate sampling distribution is the distribution of one subset of a population distribution. And these vocab words, I'll tell you what, these get very confusing because they all feel like the same thing. And I'm hoping they'll make a little bit more sense after we finish this exercise and we actually look at the graphs and we talk about it, okay? But what I want you to think about is, if you draw 20 poker chips, okay, I want you to think about what all the possibilities could be, okay? Could they all end up being red? When you draw 20 poker chips out of there, could they all end up being red? They could. Now, how likely is it? We won't get into that. Could they all be blue? Well, you don't know yet because you don't know how many blues there are. Same with greens or whites. But it could be 1 red. It could be 10 blue. It could be 4 green. Okay, you understand? Can you kind of visualize that there is a whole lot of possibilities of how you could group red, blue, green, and white chips and make a group of 20 out of those 200? If you listed all those different possibilities and you graphed them, that's the population distribution. It's huge, okay? It ends up being 200 poker chips taken 20 at a time. Picture doing permutations and combinations. Remember we did those? Okay, the P's and C's. Okay, it's a big number. But if you graphed all the different ways that you could draw 20 poker chips, that is the population distribution, okay? A sampling distribution, okay, let me rephrase it. That is the sampling distribution because you're taking the sample, okay? But this one lists all the possible ways that you could pick 20 chips, okay? You're doing an approximate sampling distribution because when we're done, we're missing what, 1 person today, so that means we have 13 of us. We're only going to have 13 dots on our graph, okay? So we are not seeing a full sampling distribution. We're only seeing the 13 subsets that we create, okay? A true sampling distribution is a graph of all the possible subsets that you could have. The population distribution is the actual value of what's in that bag, okay? All right, I'm gonna stop there because that leads us to our next exercise. So I gotta make sure, we gotta finish up our poker chips. I think we're almost done. I gotta see if I have a spreadsheet ready to go that we can enter this.